Hello everyone and welcome to this module on the introduction to continuum mechanics. So in this module, we're going to discuss the curvilinear coordinate, including polar, cylindrical, and spherical. We also have a general curvilinear coordinate, which might be discussed in another course or in some advanced courses like elasticity. Uh, but I may include it in this series of videos. It depends. But all in all, this collinear coordinates is quite important because quite a lot of a lot of problems in elasticity in plate and shell theory are solved using the collinear coordinates. For example, if you have a circular hole or an elliptical hole in a plate, and if you want to know the stress distribution around the hole, you have to use the polar coordinate system. It's much easier than just solving it in the Cartesian coordinate system. Or if you have a deformation like uh, process like rolling, so it would be easier to transfer everything to a cylindrical coordinate system. So this is important so it is quite important to have all these, curvilinear coordinates beside Cartesian coordinate system in order to make life easier and to solve and better understood problem in advanced topics in mechanics like elasticity and, as I said, plate and shell theory, or for example in impact mechanics. So let's get started by the polar coordinate. So in the polar coordinate, we're going to have an introduction to this. So in the Cartesian coordinate system, we had x1 and x2, and if we wanted to, and we also had two unit vectors. So maybe it's better to just show it with another color. So we had two unit vectors of E1 and E2, and I'm approaching this from a two-dimensional point of view, because in polar coordinate system you only need r and theta, so you only need the uh you know you need to know where the point is and the angle. This become clear as we progress. We have this, and in polar coordinate system, if you have this point, for example, here, you only need to know r, which is the radius, for example, and you only need to know the theta, so the angle that it makes, for example, with x1. So I assume that theta is basically increasing in this direction. Okay, and r is also increasing in this direction. So it is quite important how you assume these r and theta are increasing. So if we have this r and theta increasing in this direction, and you have, for example, a point like, I don't know, A, for example, here. So then you can define the unit vectors as ER. So it is increasing in this direction, ER. And then you have E beta. So it is increasing in this direction here. So if we write this ER and E theta in terms of, E1 and E2, so if we transfer ER here, so this is ER, and let me just use another color, maybe this one. So this is ER, and this is E theta. So ER is equal to, so if we just project this on the x1 axis, so it become, this is theta, remember this is theta, so this become cosine theta e1 plus this is sine theta e2, because this is theta, so this is the cosine and this is the sine. So we have also e theta here. If we project this on x1, so it is minus, minus, and remember that if this is theta here, this becomes theta here. So this is, maybe it's a good idea just to write this here. That this is theta. Okay, so this is minus sine theta e1 plus, and if we project it on x2 axis, so this becomes cosine theta e2. Perfect. And you can also differentiate this. So if we differentiate this by applying the d operator, for example, the differential operator, we call this. So der becomes, so we have cosine theta. So this becomes cosine theta d theta e1 plus, so since, sorry, cosine theta, it is minus sine theta. And then we have sine theta, so this becomes cosine theta d theta e2. And de theta is minus sine theta, so sine theta is cosine theta d theta. We have the minus cosine theta d theta e1 plus, so this is cosine theta, so this becomes minus sine theta d theta e2. And if we further, let's say, simplify this, you'll see der is equal to, so we have this minus sine theta d theta e1. So if we take out, if we factor out this d theta here, you will see that we get this. So it is basically minus sine theta d theta, oh, sorry, e1 plus cosine theta e2 d theta. And this is nothing but e theta. So this is e theta d theta. Or maybe it's better to write it as d theta e theta. And then we have this e theta. So if we take out this minus, so it becomes cosine theta and factor out this d theta. So this becomes cosine theta e1 plus sine theta e2 minus d theta. This is nothing but er here. So this is minus d theta er. Perfect. These are great, expressions here. So overall, we have d er is equal to d theta e theta, and de theta is equal to minus d theta er. So let's get to the geometrical interpretation of der here and de theta. I just use this, this caret here. It is just a habit. So the book did not follow this kind of thing because it's obviously clear here that you can write, E as bold case. So it is not going to be a problem. All right. If I just replot the first plot, but maybe a bit bigger. Or okay, so I have x1, then I have x2. So I have, for example, let's say this is the first point here. So this is r, and this is, of course, theta. And if this is actually just increased by dr and d theta, uh, this is r plus dr, and this is, of course, the theta, because it is just increased by d theta and dr. And I know that this is er and this is e theta, and of course this is er plus d er, and this is e theta plus d e theta. And remember that I put e theta perpendicular to er, but in the direction of increasing e theta. So if you assume that, for example, this is increasing in this direction, theta, then you have to define this is er and this is e theta. So remember, where you assume that r, for example, is increasing because it is increasing in this direction. So I put er in this direction. And theta is increasing in this direction. So remember how you assume r and theta are increasing, and always uh, follow this, because it is quite important to follow these kind of conventions, especially in courses like elasticity, where you want to find different components of the stress, and you don't know how uh, you know how uh, sigma theta theta or sigma r r are you want to put the direction of sigma r r and sigma theta theta, but you don't know how to put and how to assume the first or the initial direction of these kind of stress components, and you have to use these kind of conventions here so to be consistent with other solutions. All right, so here I have my ER and E theta, and there DER and D theta here. So so if I have my ER here, and you see that this ER plus DER is applied here. So we can call this as D ER. We can call this. So you see, ER plus DER is equal to ER plus DER. And for E theta, we also have the same. So this is E theta, and this is a bit twisted. So this is ER plus DE. Oh, sorry. This is E theta plus DE theta from here. So you can say that this is DE theta. It's like here. So you can also get this from here. So this is ER. This is ER plus DER. So basically this is DER. And this is basically E theta. This is E theta plus D theta. Therefore, this is D theta. Let me just write this here, E theta plus DE theta. So this is the geometrical interpretation of d and d e theta. So you can see them here, how they're changing. So a point, the position vector, maybe it's better to say position vector in polar coordinate system. So in polar coordinate system, we use just r is equal to RER. And here I use this vector. So this is bold. This R here is bold. So you have R and with this position vector here, you can specify any point. So if we differentiate this R here, so this R is a function of, R. So this is DRER plus RDER. So it is like, if you have, for example, a function of fx and g x. So if you want to differentiate this with respect to x, so you say that d of fx dx gx plus fx d of gx dx. So it is like this. So we have this, and if we just substitute this DER from here, so DER is D theta ER, D theta, was it D theta E theta? So this is dr ER plus RD theta E theta. And this is quite useful when, for example, we want to calculate the gradient or the divergence in the curl of a scalar field or a vector field or a tensor field in, polar coordinate system. Okay. Now let's get to the, the gradient of a scalar field in polar coordinate system. So, del f, or let's say gradient of a scalar field. So let f of r and theta be a scalar field. So now we're going to find the components of the stress field, and we did, similar to what we did in the previous video for the Cartesian coordinate system, we're going to apply them to the polar coordinate system. Therefore, we will be able to find the components of a scalar field, a vector field, or a second order tensor, or simply a tensor field in a polar coordinate system. So we had this definition based on the previous video that df dr is equal to the gradient of f, where f was a scalar field. And we had this df is equal to del f dot dr, where we said it is the dot product of del f and dr. So let us assume that df is, is a kind of vector, because we know that if we apply the gradient to a scalar field, or it became a vector field. So it has, for example, a component like AR. For example, we assume it to be AR, ER, plus A theta, E theta. And here we only have ER and E theta. We are working in 2-dimension. So this is we just make an assumption here. We don't know whether they exist or not. We're going to find them. And then we have dot dr. And what is dr? This dr is basically from here. So from, let's say, maybe 1, uh, we say that this is dr plus r d theta e theta. So if we apply the dot product, so this become ar dr plus a theta r d theta. Perfect. We also said that f is a function of r and theta. Therefore, if we apply the d operator, the differential operator, we have df is equal to, because it is, it depends on two variables, so we have the partial differentiation. So it is the partial differentiation of f with respect to r dr plus partial differential of f with respect to theta d theta. So here we have df equal to this and df is equal to this. So now, based on the fundamental theorem in algebra, we can say that this is 2 and this is 3. So by comparing from 2 and so by comparing 2 and 3 based on the fundamental theorem in algebra. So we see here that this is dr, this is dr. So ar is equal to partial derivative of f with respect to r here. And we have here d theta, d theta. So a theta r is equal to partial differential of f with respect to theta. Therefore, it's better to write it like this. If ar is equal to partial of f with respect to r, and we have a theta, which is partial differentiation of 1 divided by r, differentiation of f with respect to theta. So now we substitute this into this assumption we made here. Therefore, del f is equal to partial of f with respect to r, er, plus 1 divided by r, partial differentiation of f with respect to theta, e theta. All right. So next, let us move on with so this was the gradient of a scalar field. This is the gradient of a vector field. And all in polar coordinate system. So let v, which is a function of r and theta, of course, as a component vr, r and theta, which also is dependent on r and theta, er plus v theta, r and theta again, e theta. All right, so we know that dv dr is equal to del v based on the definition we made in the previous video and in the gradient. Therefore, we can say that dv is equal to del v dr. And we know that this del v, since v is a vector, so the gradient increases the order of a vector and make it a second order tensor. So this is a second order tensor. So we replace this dv by t dr. So t here is a second order tensor. And we continue with this t. We find the component of t, and this component of t actually are the components of the gradient of v. So this dr here is 1. So from 1, we have t, and dr is this expression here, dr er plus rd theta, e theta. Perfect. So this is equal to dr t er plus rd theta, because these are all the scalars. So we have te theta. And if you remember, if you recall from the very first, sessions here, we had TEI was equal to TJI EJ. So here we have TER. This is TJREJ. And here we have J equal to R and theta. So TER, J is a DOM index, so we sum on the DOM index. So we have TRR ER plus T theta R E theta. And similarly, we have T E theta, T J theta E J, and J is R and theta. So T E theta is T R theta E R plus T theta theta E theta. This also can be achieved. So the above expressions can also be achieved using. So if you recall, we said that if we have TER and TE theta, we said that we have ER and T and E theta in our unprimed coordinate system. These are the primed coordinate system. So we are going to transfer these two to the TR, TER and T theta. Then we had here TRR, and if you remember, we had TR theta, because we said, sorry, T theta R, because we said that we filling these, these like tensors in the matrix form by column. And then we have TR theta, T theta theta. And if we apply this, so we had TRR E R plus T theta R E theta. This is the same expression here. And then we had T R theta ER plus T theta theta E theta. And this is nothing but T ER, and this is T E theta. Perfect. So now we have these expressions here. All right, so we replace these expressions here. So maybe we had 1, 2, 3, 4, and 5 in 6. 4 and 5 in 6. So we have dr, dr, dv, dr, drr, ER plus T theta R E theta plus we had RD theta T R theta ER plus D theta theta E theta. So if we just expand this and just reorder everything, we have dr trr er plus drt theta r e theta plus rd theta er plus rd theta t theta theta e theta. So then we have this dr trr er, sorry, this plus rd theta t r theta er plus if drt theta r plus t rd theta t theta theta e theta. All right, so you see here we have dv as this expression here, and the strategy is just to find dv, by assuming it's, by assuming that v is a function of r and theta. We apply the differentiation operator here on v, so we get dv and from this expression here, and we compare them with the components we get here. So finally we get the components related to trr, tr theta, t theta r, and t theta theta. So also we have v, maybe I can just copy and paste it from here. All right. Okay. So dv r and theta is equal to, so this is dvr dvr r and theta er plus I have vr r and theta, and this is der plus, so the differential of this expression dv theta r and theta times this expression e theta plus v theta, this expression here, r and theta, d e theta, the differential of this expression. So here, I simply write this as dv is equal to dvr. I'm going to remove this r and theta. Er plus vr der plus dv theta e theta plus v theta de theta. Perfect. Now I'm going to substitute this de theta and der from, let's say, here. So let's call this star. So let me just change color maybe. So I have der and d theta. So I have dvr er plus vr. So der is e theta. So it is d theta e theta plus dv theta e theta plus v theta. And d theta is minus d theta er. Perfect. Now I rearrange everything. dvr, I have er minus v theta d theta er plus vr d theta plus dv theta e theta. Perfect. This is dv. So I have one dv from here. I have one dv from here. Perfect. But remember, you have here VR, not v, and v theta. So VR, which is also a function of r and theta. So if we differentiate this, so dVr is partial derivative of VR with respect to r dr plus partial derivative of VR with respect to theta d theta. V theta, r and theta, if we apply the differential operator, the differentiation operator, dv theta, this is partial derivative of v theta with respect to r dr plus partial derivative of v theta with respect to theta d theta. So I have this as, let's say, 5, 6, 7, and this is 8. So 7 in 8. So dv is equal to dvr is partial derivative of vr with respect to r dr plus vr theta d theta minus v theta d theta. This is er plus vr d theta plus dv theta, which is partial differential of d with respect to r dr plus partial differential of v theta with respect to theta d theta. And this is e theta. Perfect. Now I have this based on er and e theta and v r, and I have here d theta dr. Perfect. So I can make a comparison between, let's say, 8, this is 9, this is 10. So now I can compare 9 and 10. All right, so here I have 9. We just copy this, just put it down here. Perfect. And 10. So I have dr here, tr. So here I have dr and nothing. So tr, r is equal to partial derivative of vr with respect to r. And here I have r d theta, dr theta here. And here I have, okay, I have r, I have d theta. So this is partial derivative of r with respect to theta minus v theta. Therefore, tr theta is partial derivative of r with respect to theta minus v theta all divided by 1. Sorry, 1 divided by r, vr theta minus v theta. So then I have this dr theta r, sorry, t theta r is equal to, this is dr, so I only have here, so this is partial vr r v theta with respect to r, and then I have this theta here, r theta here I mean, and here I have the theta, this term and this term, so vr plus this partial differential of v theta with respect to theta, if I'm not mistaken. Great. Therefore, this theta here is equal to 1 divided by r, vr plus v theta with respect to theta. And if you remember here, I had this combination here. So maybe I copy this from here and I paste this here. Is equal to TRR is this here, VR with respect to R, theta R, V theta with respect to R theta is this, VR theta minus theta, and theta is 1 divided by R, VR plus theta. All right, so this is equal to del V. And as you see here, you have a vector. Now you have a second order tensor. So let's get to the divergence of a vector field. So as we already discussed, the divergence is basically the trace of the gradient of that vector. So it is just the summation of these two. So divergence of V is equal to this plus this. VR respect to R plus 1 divided by R plus theta. That's it. So now let's get to the curl of a vector field. All right, so if you remember, we said that curl of vector field is 2 times the, let's say, the dual vector. So the dual vector was coming from the, let's say, the antisymmetric tensor. So if I have this tensor, and if I can find the antisymmetric of it, which is basically TA, if you remember, it was T minus T transpose divided by 2. And for our case, basically, this is del V as antisymmetric is, oh, sorry, this is del V minus del V transpose divided by 2. So I have my del V here. Copy. Just paste it here. So if I paste it here again, so I have 1 half of this is equal to, and this is minus. So I have to swap these two here. 1 divided by R, VR theta minus V theta. Hopefully I left some space. So this is minus this become 0. This one minus this one. So it is 1 divided by R, VR theta minus V theta minus partial derivative of V theta with respect to R, and this one minus this one, partial derivative of V theta with respect to R minus 1 divided by R. Oops, this is VR theta minus V theta. This minus, and this actually cancels out with this one. And let me just shift this bit here. Perfect. Then I have the dual vector of this. And let me just put this half in here. So if you remember, the curl of V was twice its, the dual vector here. And then we had -2. If we expand this, it's 2, 2, 3, E1 plus T31 E2 plus T12 E3. And to remember this, you can write just 1, 2, 3. So you have 1, 2, 3, 2, 3, 1, 3, 1, 2. So this become T12 E3, T21 E1, T31 E2. So you can just write them here and reorder the and rearrange the order of E3, E1, and E2. So since this is basically r and theta, so we don't have any z, so there is no 3 component here. So this is 0, this is 0, this is 0, we only have this. So this is equal to, and this 2 here cancels out this, so we have a minus here. So this is tr theta E3 here. So minus, and tr theta is this component here, tr theta. Copy, just paste it down here. E3, where I guess that I made a mistake because this tr theta is basically from the anti-symmetric part. So this is from here. That was tr theta from del V. So I have this from here, copy. Let's just paste it here. And I have minus here, so this is E3. And that's it. So you can also write this as, just multiply this minus here. So you have V theta VR, and we have this -1 divided by R VR theta minus V theta here E3. And this is basically the curl of a vector field in polar coordinate system. All right, so next we have the divergence of a tensor field. Of course, polar coordinate system. So I would like to mention something here. The strategy which is utilized in this book is based on defining, some expressions or some definition, some fundamental definition uh, for some of for some of the operators, instead of just writing the concept. So for example, when we say that the divergence of, for example, v a vector is equal to the trace of del v, so this is the strategy of this book. So they define, so the authors actually they use this expression here to say that the divergence of a vector is equal to the trace of del v, in contrast to my strategy that I said that okay, the divergence of a vector, for example, it can be defined as del operator dot v. So it is like a dot operator, and then we said that okay, we have the definition of del, which is partial differentiation with xi, and we have this ei here, and it is dot. So we had vj, ej, and I use this strategy to actually to find the divergence of of a vector field. But the book utilized this strategy, and I guess it's a very nice strategy for for the polar coordinate, because it makes it much easier to grasp and to find both the concept and the, let's say, the expressions for example, for the divergence, for the curl, or for the Laplacian. And here I utilize this strategy. So the book defined the divergence of t. T is a second order tensor, of course, and here I am calling second order tensor as we create, and we have a vector here, a. So it is equal to the divergence of t transpose a minus trace of del a t transpose. You can also prove this basically for any vector a. This is just a symbol for any. And here you can simply, or I don't know, I haven't proved this, but you can always find, books where they prove these expressions for tensors. But you can also use this, expression from the book. It is expression. It is the equation 23327 in the book. So, uh, we are going to, so the strategy is that we are going to find the different components of the divergence, because this is t. T is a second order tensor, so it degrades the order of the tensor, so it becomes a vector field. So we expect that we have an r, for example, and a component in r direction, and also a component in theta direction. So we have er and e theta. So for example, we have to find the divergence of t, for example, in r direction, and also the divergence in, let's say, theta direction. So let's get started with r, where, for example, where here we assume that a is equal to er. So we have this, so we find the divergence of t in the direction of er. So if we rewrite the above equation, we have the divergence of t dot er, so it is r. It is the divergence of t transpose, and this is er minus the trace of del er. Maybe just write it like this: t transpose for the vector of er, of course. And we find different components of this expression and the next this term, sorry, and the next term, and we subtract them and finally find the divergence of t in r component, in the direction of r. And then we do the same for theta, and we find the divergence of t in theta direction. So I already mentioned that t er is basically t j r e r. So it is t r r, since j can be r and theta. So it is er, oh sorry, this is j, plus t theta r e theta. So if I have this, so t transpose e r is t r j e j. So this is t r r e r plus t r theta e theta. Great. So we have t. So next, first, maybe it's a good idea just to use this color here, And next, use another color, like, I don't know, uh, maybe purple. So purple for this one. All right. So I start with this blue here. Oops. Yep. Okay. So we have the divergence of T transpose ER. So it is basically the divergence of TRR this expression here, plus TR theta E theta. And if you remember, this is a vector. And we already mentioned that the divergence of a vector is nothing but, if I can just bring it here. So it is the divergence of a vector. So if I just copy this, and if I say that this is maybe red, all right. So based on this definition, so this is VR, and this is V theta. So from here, I can write that divergence of T transpose ER is equal to, so this is VR, so this is the partial of TRR plus divided by R, then we have VR, TRR plus partial of V theta, which is R theta, theta. Perfect. Now we have the first expression here. And maybe I need to just change its color. All right. Next, let's go to this purple car. Oops. All right. So here we have del ER. So del ER. We know that ER is basically 1 ER plus 0 E theta. Therefore, if we want to know del ER, if you remember, it was del V. Okay, it's here. So this is del V. So if we copy this, and let's just paste it here. Perfect. So let me just get rid of this. This is del V. And change this, sorry, to red. So using this too, I have del ER as, this is VR VR, and this is V theta. So partial differential of VR with respect to R is 0. So we have VR with theta, because these are constant, so this is 0. This is 0. V theta is basically 0, so this is also 0. This is 0. This is 0. We only have 1 here divided by r, VR, which is 1. So that's it. And then next, we need to multiply this by t transpose. So if I just del ER t transpose is basically 0, 0, 0, r. And if you remember, this was t r r t theta r t r theta t theta theta. I hope that I wrote this correctly. So if we multiply this, this is 0. This is also 0. It's 1 divided by r t r theta. This is 1 divided by r t theta theta. And this is the trace. So the trace of del ER t transpose is basically 1 divided by r t theta theta. Perfect. Now I have my first expression here. This is this. Copy. Just paste it here. Minus, because I have a minus sign here. 1 divided by r t theta theta, which is this expression. So this is the divergence of t, the r component. All right, so now let's do this for divergence of t for theta component. So what I get is this, basically. So copy this, paste it here. So I have the divergence of t transpose. Now A is e theta minus the trace of del e theta t transpose. Yes. All right. So I have t transpose e theta. So t e theta was basically t j theta e theta. Therefore, t transpose e theta is t to theta j e. Oh, sorry, this is j ej. So this is t. J can be r and theta. Theta r e r plus t theta theta e theta. All right. So I have this and the divergence for this. This is v r and this is v theta. And the divergence of t transpose e theta is basically partial differential of VR. So this is t theta r with respect to r plus 1 divided by r, partial differential of v theta, which is t theta theta by theta plus VR, which is t theta r. All right. Then I have e theta, which is basically 0 ER plus 1 E theta. So I have del E theta, which is equal to, del E theta is equal to, So I have partial, this is VR, and this is V theta. Maybe I need to just push it a bit down, del E theta. This is partial VR, which is, so every VR is 0, so this is 0. So 1 divided by R minus V theta, so this is minus 1 divided by R. This is 0, and this is also 0. Then I have T transpose here. Del E theta, T transpose is equal to this times TRR, and this is T theta R. T theta R, this is R theta, theta theta, is equal to this divided by this, minus 1 TR theta, minus 1 divided by R T theta theta. This is 0 and this is 0. And the trace of del E theta, T transpose, is minus 1 divided by R TR theta. Great. So now we have this expression here. Copy. And this is the divergence of T theta. Paste. Here, minus minus becomes plus TR theta, which is the same as the equation 233.33. Great. Let's get to the Laplacian of scalar field. All right, so we already mentioned that the Laplacian operator is del 2f, which is del dot del f, and basically this operator was defined as divergence. So this is the divergence of del f, of course. And we know the gradient of f. So del f is already equal to partial derivative of f with respect to r. And of course, f is scalar field. Er plus 1 divided by r, partial derivative of f with respect to theta, e theta. So here we have to calculate this divergence, and this is a vector. We already know this. So this is VR and this is V theta. So the divergence of a vector field is defined as partial derivative of VR with respect to R plus 1 divided by R, partial derivative of V theta divided by with respect to theta plus VR divided by R. So based on this, the divergence of del F is equal to partial derivative of VR, which is, okay, so this is F with respect to R plus 1 divided by R, partial derivative of V theta, it is by R F theta plus 1 divided by R. VR is this. Perfect. We need to further simplify this. So this is second partial derivative of f with respect to R plus 1 divided by R. And since this R here has no dependency on t, so it can taken out. So second partial derivative of f with respect to theta plus 1 divided by r, partial derivative of f with respect to r. And remember here that f is a function of r and theta. That's it. All right. So let's get to the last one, which is the Laplacian of a vector field. So for this one, we use an expression which is given in the book. So del 2v, where v is a vector, of course, is del dot divergence of v minus curl of v. This is equation. It appears that no, it is not an equation, but it is given in the book. But this can also be written as so del dot v here. So we know that this is an operation. This is a divergence, and curl can be written as curl of curl del v, something like this. So here, let us see what we expect here on the left-hand side of the equation. Del cross v gives us a vector, and del cross a vector finally gives us a vector. Del dot v is basically the divergence, which is a scalar field here, because v is a vector. And here, the gradient of a scalar is also a vector. So finally, a vector minus a vector gives a vector. So we expect to give something like a vector here, something which is like, del to v r and del to v theta, something like this. All right, let's start with this one. All right, so here we have the divergence. So we start by, let us start by del dot v, where we call it divergence of v. So del dot v, which is maybe divergence of v, is del dot v. This is equal to partial derivative of v r with respect to r plus 1 divided by r partial derivative of v theta partial derivative with respect to theta plus vr divided by r. This is a scalar, right? And the gradient of this scalar field is basically, and let us say that del f is here, right? So if I just copy this and maybe paste it here. So now we know that therefore we have del dot del dot v del the gradient of del dot v is equal to partial derivative of r, and this whole here is f. This is f. So partial derivative of vr with respect to r plus half of partial derivative of v theta plus vr r e r plus 1 divided by r partial derivative of f here. Again, f is again this plus vr r whole with respect to theta. This is e theta. Okay, let us simplify this. So we have the partial derivative of this. So it gives second partial derivative of vr with respect to r2. And here we have this whole expression here. So this whole here, we have to take the derivative of this red one with respect to r, right? Okay, so this is minus 1 divided by r squared times this part. So we take the derivative of this part first with respect to r times the second one. And now we have this, so it is plus 1 divided by r. So we take the derivative of the second one. So it is the second derivative of v theta with respect to r and then theta. So it is not important whether you take the first derivative with respect to theta and then r. So it is the same. So these are the same. These are both equal. And then finally I have this one. So this is minus 1 divided by r squared, or VR here, plus 1 divided by r, partial derivative of VR with respect to r. And this whole here is ER plus 1 divided by r times this one. Okay, so this is the first one. So it become second partial derivative of VR with respect to theta and r plus 1 divided by r. Since this one is not a function of theta, so we treat this like a constant, so it can be taken out. Then we have second partial derivative of v theta with respect to theta plus this one is again the same. So we have 1 divided by r, partial derivative of vr with respect to theta, and this is whole e theta. Great. So next, we have this curl of v. So we know that del cross v, we already calculated this, is partial derivative of v theta with respect to r plus v theta with respect to, divided by r minus 1 divided by r, partial derivative of vr with respect to theta e3, if you remember. And here we're going to take the curl of this expression here. And since we have E3 here, so the third dimension is involved. Now we have to use the curl from the cylindrical coordinate system. So since E3 is now involved in calculation or in calculating del dot del cross V, we borrow equation 234.7 from the cylindrical coordinate system. Okay, and we will prove this. So here the curl of let's say a vector, because this is a vector, the curl, let me write it with another color, of v. So to make sure that these are two different things. So the curl of v, yes. And maybe I write it like this, or maybe just leave them this. So this is, or maybe the curl of v like this. So this is equal to 1 divided by r, partial derivative of vz with respect to theta, partial derivative of this v theta with respect to z er plus partial derivative of this vr with respect to z minus partial derivative of v z with respect to r e theta mm, plus partial derivative of this v theta divided by r plus v theta divided by r minus 1 r partial derivative of vr with respect to theta e z. So, all right. So we know here that our expression here is not a function of, let's say, this ez, which is e3 here, same as 3 here. This e3, maybe I can write this as z, all right? So we know that v theta is not a function of z, so this is 0. Vr is also not a function of z, but vz is a function of theta here. This is vz, or let's write it like vz. So here vz is a function of r, we can see it, because each of these vr and v theta, they are a function of r and theta, right? Then I don't have any easy here. So because we are in the polar coordinate system, so this is also 0, 0, and this is also 0. So there is no easy component. So we substitute, let's say, this one, or let's say, I don't know, maybe 15 is better, and this is 16. Sorry, show, so just to make sure that they do not coincide with the previous numbering. So by substituting 15 in 16, del cross v is 1 divided by r, partial derivative of vz, where vz is the partial of this is vz here. So it is partial derivative of v theta. This is vz here, where we had it from here. V respect to r plus v theta divided by r partial derivative of vr with respect to theta e r minus partial derivative here of vz with respect to r. So we have again this expression here. And this is e theta. Great. So if we simplify this, get 1 divided by r. So this become second partial derivative of v theta with respect to theta and r plus 1 divided by r, because this here we only have v theta, which is a function of theta. Great. Minus 1 divided by r, second partial derivative of vr with respect to theta er plus, oh sorry, minus. So this is respect to r. So this is second partial derivative of v theta with respect to r. So if this is, okay, this is minus. So so I tried to do everything and then try to factor out this minus, and then I multiply everything with this minus. So I just leave it here, minus. So then I have minus 1 divided by r squared v theta here. And then I have plus 1 divided by r partial derivative of v theta with respect to r. Then I have this one minus, so minus minus becomes plus. Second partial derivative of this. No, sorry, I made a mistake. It is this one. So this is minus 1 divided by r, second partial derivative of vr with respect to theta. Great. And now I multiply this minus. So this is minus plus minus plus. So plus this e theta. Great. So now I have this, the second term, as well as the first term. So I simply pick this ER part here, copy, and then paste it here. So this is del VR. And I also have this here. Let me check if I haven't missed anything. No. Then I have this expression here, copy, and then paste it here. All right, so I have to make some modifications here. This is ER is plus, oh no, this is minus. So 1 divided by R, because here we have minus here. So minus, this is also minus R squared, this is plus, and the whole is ER. So if we rewrite this, you'll see that, let me see. So del VR is equal to, so I have this term here, second partial derivative of VR with respect to R. I have V theta so minus 2 divided by R squared V theta. So I already had this one in this one. Then this one cancels out with this one. Minus VR divided by R squared. Plus 1 divided by R, partial derivative of VR with respect to R. Minus 1 divided by R squared, partial derivative of V theta with respect to theta. So we have 1, 2, 3, 4, and 5 terms, while in the book, plus partial derivative of VR, second partial derivative of VR with respect to z squared is also written, but this is not included, so it's just a typo. In equation 2, in equation, so NB, in equation 233, 40. So this second partial derivative of VR with respect to z should be removed. is just a typo. So just remember this one. This is the equation 23340. Great. So next we have the other component, del v theta. So we have this from here, copy, just paste it here. And then we have this expression from here is from the second term. So, oops. And then paste it here. So you have to get rid of this. And this one. Okay, so 1 divided by r. Let's just multiply this r squared. And I have, so plus minus, so this becomes minus and e theta. Great. So finally, what I have here, oops, is equal to, so I have 1 or it's, I think that I made a mistake here. So this is the partial derivative of this expression with respect to r. So this is partial derivative of r, this theta, and this is r, this is theta. So, and also we have this minus sign here because we have the first expression minus the second expression here. So this becomes plus, minus, plus, minus. So this can be cancels out this one. So I have 1 divided by r, second partial derivative of v theta divided by, sorry, with respect to t theta plus 1 this is squared, 1 divided by r squared, 1 divided by r squared, partial derivative of Vr with respect to theta. And here I have and there might be another typo here. So I have the derivative of this with respect to r, which is here, the derivative of this with respect to r, which is v theta, and also I forgot to include so the first one is minus, so this is mine plus, and then I have a minus, so this becomes plus, so minus. So I have minus minus plus, and I have a minus here, so it is 1 divided by r squared, partial derivative of Vr with respect to theta, plus, now I have this one, so it is minus 1 divided by r, but I have a minus here, so it becomes plus, and I have 1, sorry, it is this one. So it is the minus of so minus times minus plus 1 divided by r goes here, and I have the second partial derivative of Vr with respect to r and then theta. Great. So now I have this one. So I copy this and I paste it here. Right, great. And this is minus. So this term minus this term here, and it is E, sorry, it is E theta. Great. All right. So I have minus here. So minus minus, this become plus, minus plus plus minus. This cancels out with this one. I have 1 divided by r here, 1 divided by r squared here. Great. I have plus partial derivative of v theta divided second partial derivative of v theta with respect to r. So I have minus 1 divided by r squared v theta. Then I have 1 divided by r. Okay, so 1 divided by r, partial derivative of v theta with respect to r. And then I have this, which is same as this. So this is 2. All right. Which is the same as equation 23341. All right, and this actually finalize our calculations of the gradient, divergence, curl, Laplacian, in the polar coordinate system.